we have been examining sequential MSI elements. Among those, we've got registers and counters. We have seen registers. We have seen asynchronous counters. Now we will be seeing synchronous counters. Synchronous counters, to differentiate it from the asynchronous ones, in the synchronous counters, all the memory elements, clock inputs, are connected to a central clock. So it is run by this central clock. In the asynchronous counter, it wasn't like that. So you see a counter here, and this counter, we've got one input here, which is, it's called count. So if I clear this, you could see it much better maybe. So this input here is called count. And this is clock input. As you see, clock input is connected. Let me show it like that. Clock input here connected to this, to this, to this, and to this. That means central clock, that is. The output, we've got 4 outputs, 1, 2, 3, 4 outputs. And we're going to count the clocks. So any clock pulse comes here, at the output we are going to see a number which is increased by 1. So that is counting, and it is called synchronous counter. So this frame here shows the integrated circuit. All these elements are in the integrated circuit. So let me clear this area as well. Okay, all the in integrated circuit I said. So they sell this in the market. It is available. You can buy that. There is another output here, not seen properly. Let me throw it in different color. That one. That shows you output 1 when the numbers is higher number seen here. That means 1, 1, 1, 1, 15. When you see 15 here, it gives you a message to the next counter, binary counter, because this counts up to 15. But normally you might need a counting after that. So how are you going to do it? As you know that if you've got 4 bits, if you are counting and you come to the 111, the next count is going to be this, isn't it? So that means that's going to be next 4-bit counter additional. So any output coming out of this 1 tells you that 1 tour has been finished in the previous one. That means from 0 to 15. So that means you've got 15 inputs, 16 inputs. When they come in, then that means it is full. You're going to see 15. And then when the last clock pulse comes, it's going to be 0, 0. The next 4-bit clock input is going to be this input. This clock input is affected this new integrated circuit. That's clock input is going to be. That means that 4-bit signal is going to be increased by 1. When this 4 least significant bits are full, there's going to be 1 clock pulse here. Another set of 16 clocks here done, then this is going to be increased by 1. So that means you can extend your counting by additional integrated circuit that you have here. So this additional integrated circuit clock input is going to come out of this output of the previous counter. Now let's examine now how this counts. So you could do design of it by using the classical design method that we have already examined. Because this is synchronous, therefore you can use the design technique. But you don't have to do this design here because we are saying that this is available as an integrated circuit. We are going to examine how this runs. Does it do the counting or not? That is analysis. And then by using this, what you could do is the second part of it. So we've got 4 outputs. Our input is clock, and count is, when count is 0, let's examine what does this do when count input is 0. Let me write it in which color shall we do it? Let me do it this color. Count 0, count input 0. What happens is this, count 0 means this is 0, that is 0. And when this is 0, the output is 0, 0. That means that's going to be 0, 0. All the JK flip-flop inputs are going to be 0. Here you see the JK flip-flop definition relation. In this definition relation, it says when the inputs are 0, 0, there is no change at the output. So no change. When count input is 1, what happens? Let's draw the timing diagram for this. So we are going to count the clock pulses. Let me draw the clock pulses first. So if you look at this clock input here, it has no circle in front of it, so it is going to be a raising edge or positive edge sensitive. So clock pulses, let me draw these clock pulses. I'm going to draw a few clock pulses. Second, fourth one, third one, and fourth one, and fifth one. It goes like that. I'm not going to draw all of them, but you could, okay. So positive edge sensitive, so I put this positive edge here, or not here, here, positive edge, positive edge. So changes is going to happen on that edge, no other edge. So the output is A0, A1, A2, A3, so I draw here, that is A0, A1, so let's create this area, and, oh not this one, sorry. So that is A2 and this is A3. So A0, A1, A2, A3. These are the outputs, how we are going to observe the outputs before the clock pulse comes. So the changes is going to happen here. So let's say changes in, sorry, so I could use this for the other ones. Changes is going to happen on this edge only, isn't it? Make this one like that, okay. I cannot delete now, maybe I could do it. A bit clearer. Okay. So before the first clock pulse, let's say our outputs are 0, 0, 0, 0. When the clock pulse comes, what happens? When count is 1. So count is 1, that means, let me clear these zeros here. That was when count is 0, isn't it? Now count is 1, so make it count is 1. So if count is 1, this is going to be 1, 1, isn't it? Just by looking at that, that means when count is 1, the JK input continuously is going to be 1. So JK input, that means the first JK input, that represents the least significant bit. You can say that when the inputs are 1, 1, your state, the next state is inside here, toggles, isn't it? When it is 0, it becomes 1. When it is 1, it becomes 0. So if it is 0, it's going to be 1 until the next clock pulse comes. When it is 1, a clock pulse comes, it's going to be 0. So the least significant bit is going to be like that. No problem there. Is this what we are expecting from accounting? Yes. I'll show it to you. If you write the numbers counting here, let me do the counting here. 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. You see the least significant bit here. I'll use a different color. Let me red. This least significant bit goes as zeros and ones, isn't it? When you are counting from 0 to 7, let's say, it is 0, 1, 0, 1, it goes. So you see that 0, 1, 0, 1 is going like that. If you look at the second JK memory element output, how it is going to change. So since this is 1, so that is 1. And before the first clock pulse, the A0 value is 0. So that means that is 0. So although the count is 1, the output of this AND gate is going to be 0, 0. Isn't it? When input is 0, 0, that means no change. So for the second memory element output is going to be this 0 after the clock pulse, first clock pulse. Right? What about the second clock pulse? Before the second clock pulse, the A0 value is 1, isn't it? So that is 1. So I'll change it now. That is 1. So count is 1. So output of this AND gate is going to be 1. So that's going to be 1, 1. When the input is 1, 1, when the clock pulse comes, that's going to toggle. So you are here, and before the clock pulse, your output, your state was 0. So when it toggles, it's going to be 1, isn't it? So in here, it's going to be 1. That is 0, that is 1. So what about the third clock pulse comes? What's going to happen? When the third clock pulse, before the third clock pulse comes in, my A0 output is 0. So that is 0, isn't it? So change the color to green now. When this 0, although the count 1 is 0, the multiplication of those two is going to be 0 here. So it's going to be 0, 0. JK input is going to be 0, 0. That means no change. Before the clock pulse, our state was 1. No change means it's going to stay as 1. So if you look at the third one, before the clock pulse, our output, let me change the color once again. Our output is going to be 0 here, isn't it? Third clock pulse, before the, this is the fourth clock pulse, sorry. So third program, we have done it. So fourth clock pulse, so our A0 value is 1, not 0, but 1. So let me clear this. This is not 0. So if you look at here, before the fourth clock pulse, my A0 value is 1. So that is 1. So this one is going to be 1, 1. When it is 1, 1, it's going to toggle. So that is going to toggle. It was 1 before, so it's going to be 0 next. So you can continue like that. So when you come to this one, you're going to say that what is the previous value of A2 in order to determine the third JK flip-flop input. So if you continue like that, you can fill up all this. Now if you look at this second line here, you see that there are, the order says 2 zeros, we've got 2 ones, 2 zeros. So if you look at this now, make it color black. So this second bit here, when you are doing the counting, it is 2 zeros. Let me show it like that. It has 2 zeros here, 2 ones here, 2 zeros here, 2 ones here. So 2 0, 2 ones, and 2 zeros again. It goes like that. So if you put them all together, if you draw the A2 and A3, you're going to end up with 0, 1, 2, 3, 4, 5. That is counting. So what this circuit does the counting. I left something to you as well. What we are doing a time diagram in a sequential circuit. We have done it in the analysis of the sequential circuit, which includes SSI elements. So you could be able to do this your own as well. To finish up, I mean. So the second one is an up and down counter. So I'm going to leave this one to you as well. When the up counter is 1, the other one is 0, this circuit counts up. So it's going to be now this circuit, let me do it like that. So this is an integrated circuit. And this integrated circuit has some inputs, of course, and some output as well. So this A0, A1, A2, A3, the output. These are the inputs. The other input is clock. So we are counting the clock pulses, and when the input is 1, 0, up and down input, it counts up. If it is 0, 1, it counts down. So it is counting up and down. So in practice, you might need this, isn't it? When you are talking about the traffic lights, you are counting down. So it says how many minutes left to light turn to green. It is, you've got to give that information to the passengers. So we are counting down in traffic lights. But if you are counting the number of persons coming into the building, you are counting up. So you might need both of them. Maybe I should have mentioned in the previous one thing else. So you see that is the counting. If you take the outputs, the outputs taken out is the state variable itself. If you take out the prime of the state variable, so that means if you take those out, so what you're going to see is the negation of the other outputs, isn't it? Negation of the outputs, if I write it down here, it's going to be 1, 1, 1. It's going to be 1, 1, 1, 0, and 1, 1, 0, 1. So that is 15, 14, 13. So that means if you take the outputs from the prime of the state variables, then you are counting down. If you take it from the state variables itself directly, you are counting up. So you could see up and down counting. Maybe it's good for you to think about if this is a positive edge sensitive memory elements. If it is negative edge sensitive, what happens? So you do it your own. You would see something that I just explained. So it's a good question for you. Up and down counter. So okay, the previous one, we changed the output. That means, so this is up and down counter, but up and down counter, the number of output is just 4 in this one. If you use the other one, if you make it up and down, you're going to, the integrated circuit is going to have 8 outputs. If you increase the number of outputs in an integrated circuit, the cost increases as well. So that's they produce this type of integrated circuit as well. In the number of outputs here, that means the number of output terminals is less. That means less the cost. So that's going to be cheaper than the other one. If you want to make the other one up and down counter. Okay, this is universal counter now. Synchronous universal counter. That it is written in Turkish, so I'll make it in English. In this one, synchronous universal counter. So this is a box. This is an MSI element. Let's count the inputs. So 1, 2, 3, 4 inputs we've got here. And data in when says it does the loading. So if you remember, we have done the loading operation in registers. So you could do the loading operation in counters as well. So it says data in. That 4 tells you there are 4 lines for representing the data, 4-bit data here. So another 4. So altogether number of inputs is 8, isn't it? 8 inputs. These are external inputs. What are the internal inputs? Inside there are 4 memory elements. I'll show you. Inside this universal synchronous counter, we've got 1, 2, 3, 4 memory elements. So if there is 4 memory elements in it, that means you got 4 state variables. So another internal inputs is going to be 4 internal inputs, which are state variables. So the total number of inputs is going to be 12. So the number of outputs, you've got 4 outputs as counting, and you've got a count out as well. This is a count out, as I explained before. When you count up to 15, you're going to get another one here to make the clock input or the next integrated circuit. That means you're continuing the counting. So in here, you're counting up to 15. If you put another integrated circuit here, you will be counting to that number, isn't it? If you've got 2 of them. If you've got 3 of them, it's going to be another. So you can do the counting up to this number by connecting the universal synchronous counter in serial, as we have done it here. Now, so inputs, the outputs, 5 outputs we've got. If you want to draw a truth table for this universal synchronous counter, so you're going to put 12 variables here and 5 outputs here, outputs and inputs. So the number of rows that you're going to have here is going to be 2 to the power 12. That number is equal 4096. So not easy to do that, isn't it? So that's why we are using function table rather than truth table. That's truth table. And instead of this, we're going to use function table. You see how simple it is. So what we've got in that function table, we've got the inputs clear, clock, load, and count. So these are these 4 inputs. And write the function instead of writing the output. It says now when the clear is 0, whatever the other inputs are, not important, whatever their value is, your output is going to be 0. So this line represents half of these lines, just one of them. That means 2000 24 lines is going to have output 0, and you're going to put all that in. Understand? So that is good news for the representing point of view. So when the clear is 1, there are 3 cases. When load is 1, count is not important. When load is 1, when the clock comes, it does the loading. That means that 4-bit data comes to the output of your counter on the positive edge of the clock pulse. In here, still clear is 1, and load is 0, and count is 1. In this case, it does the counting. Count next binary state. When clear is 1, clock is raising edge, load 0, and count 0, no change. That means no counting. So there are 4 functions which is done by this synchronous counter. So just 4 line is enough to represent this truth table as a simple table, which is function table. So what is inside? Let's come to that. Inside we've got this. You see the count input, load input, clear input, and clock input. Just start from the clear. When the clear is 0, the clear goes all the JK flip-flops, clear inputs, you see. So I can put a color here. You can follow it. Maybe I can do it like that. That clear here, that line comes to this JK flip-flop clear input. It also comes this JK flip-flop clear input, clear input, clear input. That small 0 here, a small circle, let's say, tells us that when this input is 0, that clears. So that makes the JK flip-flops output 0. So that means what is set here is none. So when the clear is 0, function is outputs are 0. So let's follow the other one. I'm going to show one of them. You could do the rest of it with your own. So loading, for example, this clear is 1. So that's going to be 1. That means JK flip-flops are going to work, isn't it? When this 1, it doesn't do the clearing. So load is 1, it says. So let's use different color for that. Load, make it green color. Load is 1. So that is 1. When loading, count is not important. We see how it is not important now. When load is 1, output of this NOT gate is going to be 0 here. So this AND gate output, whatever the count values, is going to be 0. So that means this is going to be 0. That's going to be 0. So that is going to be 0. Isn't it? So because that is 0, coming here, that is 0. And that is 0. So this is AND gate, so the output is 0, so this too is going to be 0. This is output of this AND gate, whatever the other inputs are, it's going to be 0. And that's going to be 0. When load is 0, okay, when the output of this NOT gate, if the input is 0, then output is going to be 1. So input is going to be 1 here. The output of this AND gate is going to be 1 times I0, gives you I0, isn't it? So I0 plus 0 is going to give you I0. If you look at the other one, it says this input is 1 to this AND gate, and the other input to this AND gate is going to be I0 prime. So that's going to be I0 prime. So output is going to be I0 prime. I0 prime plus 0 gives you I0 prime here. So JK inputs, J is I0, K is I0 prime. So that means, so you could follow all this. If you do it, you're going to see that this is going to be I1 here for the second JK flip-flop, I1 prime, I2 prime, and I3 prime. The meaning is this: when the J and K inputs are I0, IZ prime, that means opposite to each other, isn't it? Opposite to each other happens in this two cases. That's the definition relation of JK flip-flop. So in here, JK values are the same. When it is opposite, you are on this, either on this column or in this column. So if you are in this column, the value you observe at the output of the flip-flop is going to be 0, which is the same as the J output, J input, isn't it? So in here, if the output is opposite to each other, the output once again is the same as J input. Conclusion is this: if the inputs are opposite to each other value, then J input is transferred to the output. So when the inputs are opposite to each other, which is this case, J input is transferred to the outputs. A0 we're going to see here, J input I1 we're going to see here, I2 is going to see it, and I3 we're going to see. That means loading, isn't it? It says here input loads. So I have done this, so you could do the others. No change one is going to be simple, so you could do this too, similarly as I did it for the second line. So that is only the analysis that you are doing, so you would be able to you are capable to do that. The one thing I've got to remind you, that is what we see inside the MSI element. So normally we are not going to go inside the MSI element. We are going to use this element in order to do the counting. So that means if you got one of these universal counter, 4-bit counter, so that is 4-bit counter. This is the one inside. If you put another one next to it, but if you take this output, that means that 15 number that you are seeing here, and another clock pulse came in. One output comes out of here, one output comes out of there, comes out of this one, and goes into the clock input of your second MSI element. So this, if this is 0, 0, 0, it counts up. 1 up, it counts 1 up, means it's going to be 1, isn't it? So it's going to be, this is after that, it's going to be 0, 0, 0, and that is increase 1, so it's going to be 16. It was 15, it's become 16. Then this is going to start to counting again up to 15. When it comes to 15, another clock pulse is going to come here. That's going to be 2, isn't it? So it goes like that. So you are increasing this after 16 clock pulses. You are increasing this one more. So you could extend your counting by adding these 4-bit MSI synchronous counters next to each other. If you do that connection, you could get higher numbers. So for example, if you got 4 of them like that, the highest number that you're going to see is going to be this, isn't it? That is full, that is full, that is full. So you can calculate what that number could be. But I can tell you what it is. That is 4, 8, 12, 14, 2 to the power 15 minus 1 is that number. So you check it. That's the question mark for you. The next one, the usage of these counters. One of them is, I said to you, you can use these MSI elements to increase your counting number. The other thing is the binary coded decimal. If you remember, in the asynchronous counters, we use binary coded decimal counters as well. Now we are saying, because of the additional control inputs that we have in this universal counter, we could transfer this binary counter to a binary coded decimal counter. How we are going to do it, there's 2 alternatives seen here. Look at this alternative now. It used the load input. So this is a counter When this counter counts, the count input is 1, clear input is 1, so count is 1, clear is 1, so we are here, isn't it? So we are going to check load now, load input, whether it is 0 and 1. If it is 1, loads the inputs. If it is 0, it counts. So assume that at the beginning that was 0, so the output was 0. This does the counting. Counting up to what? So we're going to check when this load value is changing from 0 to 1. So look at 1. This is, if this is 1, and if this is 1, that's, so assume that these are 0, 0. So that means when you reach the number 9, that's going to be your input, isn't it? When you get this input, your AND gate output is going to be 1. So that means load became 1. When load became 1, when the clock pulse comes, so it goes to loads the input. If you look at the load input is 0, so after 9, you're going to see 0, 0, 0, 0 because of this 1. So you see 1 at the output. When this 1 load comes in, that input is going to be loaded in, so it's going to be 0, 0, 0, 0. It is binary coded decimal counting. Just remind you, if you got 759 something like that, binary coded decimal, it's going to be this, isn't it? 0, 1, 0, 1, 5 and 0, 1, 1, 1. So you are representing each digit in decimal number by a 4-bit binary number. So in one digit, the highest number that you could see is 9. After that, that's going to be 760, isn't it? So that's going to go to 0, 0, 0, 0. So you're going, after 9, you're going to see 0. So this is what we have done here. That is one method. The other method is seen here. It uses the clear control input to do this job. So you get clear input. So in this case, count is 1. Count is 1. So that is the case. Count is 1. Load is 0. Load definitely 0. You've got the clock pulse. And clear, we are going to check it now, how it is changing. So let's check now. If you look at this input now, this is an AND gate. It becomes 1 when the inputs are 1, 1, isn't it? The output is going to be 0. So when the clear is 1, it counts. So when the clear is 1, this is going to count. When it counts, it's going to count 0, 1, 2, 3, 4, 5. So when it comes to this 1, 0, 1, 0, what happens? That is 10, isn't it? This 2, 1, multiply 2, 1, AND gate, it gives you 1. Not of this AND gate gives you 0. So when this 10 comes in, then that's clear is going to be 0. Clear is going to be 0 without waiting for the clock pulse, because there's an X here. Whatever the clock pulse value is, that means the output immediately becomes 0. So this is, your output is going to be 0, 0, 0. So normally after 9 we've got to see the 0, but we have seen a 10 here. So explanation is this: how long we are going to see this 10 here is the delay time of this element, isn't it? Because when the output is 0, then this becomes this 10 becomes 0. So the time interval that you observe, that number, is in the range of the delay of this element, which is in the range of microsecond. Microsecond is a time interval that you cannot follow it by your eyes. So you're not going to see that. So after 9, when the clock pulse comes, you're going to see that 0. Very short time, not observable. Okay, so this is another binary coded decimal counting. So these are two applications that, so you see these control inputs gives you some facilities to do what you wanted to do. So the control inputs are the inputs that we could observe in MSI elements, not the SSI elements. So that is the flexibility of the MSI elements which are available in the market. So another application of the counter is given here. If you remember in registers, for example, in serial ladder, let's say you've got a box here, serial ladder, you're going to add the numbers in serial here. How are you going to do it? You're going to use registers. So assume that this register has got 8 bits, 8-bit register. Why we've got this register? When you put in the number to add them up, this number is going to be applied in serial to the input starting from the least significant bit, isn't it? One by one after another, you've got to apply these inputs to your circuit. So not easy to do it by hand. You're going to do it automatically. How you can make it automatically? Because you know that there is a central clock pulse here. So our circuit runs with that central clock pulse because we are dealing with synchronous circuits, synchronous sequential circuits. So in this case now, I would like to have my circuit to run for 8-bit time interval and then stop. If this clock pulse comes continuously, so whatever maybe the 8 bits are going to be finished here, but your circuit is going to continue to run. So it's going to assume your input 0, 0 and do or counting whatever it does this circuit. That means serial ladder is going to give you some values for the 0, 0 input, because after 8 bits you've got zeros. So it's going to run continuously if you don't stop it somehow. How we can stop it? So you can stop it with this is a clock pulse. You see, I'll change it, I'll show it here. If you've got these clock pulses, so this continuously comes in. But if you run your circuit here for 8 clock pulse only, you need a pulse like that, which includes 8 clock pulses in it. It is called word time signal, or you might call it clock pulse control signal. So if you multiply this signal with this clock pulse, you are going to see 8 clock pulses only applied to your circuit. So what I am saying is this. Let's say you've got an AND gate, one of these AND gate input and 2. So what we are going to see here, I am saying if this input is this continuous clock input, so I can show it to you by this color. So that is input, this input. Okay? So if I apply this pulse here, this pulse is this pulse, you see, I am drawing it. It has got a time interval which includes 8 clock pulses in it, and it becomes 0 here. If you apply this signal to this input of your AND gate, what you're going to see at the output, you're going to observe only this 6, make it different color. this 8 clock pulses seen at the output here. Okay, so what it means, if we apply this signal to that clock here, this circuit is going to run for 8 clock pulses and stops. So you can see the result of your at the end of your working time. That is the working time or work time signal. Okay. Now, how we are going to find this signal? So this signal we are talking about now. How we can get that signal? So let's clear this area once again and examine this circuit does it. If you look at this circuit, you've got a counter here. So how this runs, beginning signal, if you apply a beginning signal, this is SR type memory element definition relation. SR, and that is small y. So I'm going to use this definition relation because we've got a SR flip-flop here. So we are saying at beginning signal, you're going to push a signal to that input. So that is this one you are applying here. This. And our input is 0. So when you apply 1, 0, whatever your state is, your output is going to be 1. So that means SR type memory element output is going to be 1. So this is the output, that Q here, that output, you see, it became 0 and it became 1 because of that output. So this is the next state value. Whatever your present state value is, next state is going to be 1. So it became 1 here. So, and then you've got 0, 0 input here. 0, 0 input means this definition relation. So that means no change in this state. No change in this state means it's going to stay 1 continuously. Until when? You see the second input here, R value, comes from the output of a counter. This counter is a 3-bit counter. So when this is 7, my output, the AND gate output is going to be 1. So when this 7 clock pulses comes, my counter is going to show you 7. My AND gate output is going to be 1. That is, which is also the R input. So R became 1. So S is 0 and R 1. S 0, R1. That's this case, isn't it? So in this case, it says your output becomes 0. Your output becomes 0. That means it's going to be 0 here. So what we have done here, at the output of this SR memory element, I'm going to observe that signal. That's the signal that I am looking for. So multiplication of this signal with this one, at the output of that AND gate, you're going to see this 8-bit clock pulses only. Before that, no value is 0. After this 8 clock pulses, you're going to see 0 at the output of this AND gate. That means you are running your circuit for only 8 clock pulses. So that is, you can consider an application of the counter. So application of a counter could be used in the traffic lights, could be used the number of people coming inside a building. So when you're coming to our university, in the gates, the number of people is counted there. So it is a counting business. So in practice, we need this type of elements. That's why they produce these elements. Ring counter, I am going to leave it to you. There should be something for you left as well. And this I should mention a bit. You see, in general, the MSI elements, the manufacturer gives you definition relation of some information about their products. How do they give it? They give it as function table, not truth table, function table. That is the function table of a register. this, if you look at this function table, you don't see the time. You see, time is not included here. In here, they give you this time diagram in order to define their product in the time axis. So if you consider this axis time, so you could see what time instant there is, you could observe an output change. So they give you this diagram. So when you see this diagram, don't hesitate. So it is just a transformation of that information to this. So from time to time you can look at it and see exact time instant when the change happens. So this is going to be additional. So you got the function table plus this timing diagram in order to define or to understand the behavior of the MSI elements which are available in the market. So that is the end of this video then.